Have you ever wondered whether one of the most familiar sentences in all of science is also one of the most misleading? We are told from childhood that light moves. It travels from the sun to the earth. It races across the universe. It is the fastest thing that exists. And in one sense, all of that is true. By our clocks, light takes about 8 minutes to come from the sun to your face. Laser pulses cross a room in a tiny fraction of a second. Telescopes collect light that began its journey billions of years ago. But tonight, we have to place that familiar picture under colder and more careful scrutiny. Because physics has a habit of doing this. It takes a sentence that seems obvious, and then it asks a more precise question. Not whether it sounds right, but whether it survives contact with the deepest structure of the theory. And when we ask that question here, something unsettling begins to happen. The phrase, light moves, starts to wobble. Not because light is slow, not because it is motionless in some naive sense, but because light does not behave like any ordinary moving object at all. A stone can rest. A train can speed up. A planet can be tracked along a path. A thrown ball moves through space while time passes for it continuously along the way. But a photon does not fit cleanly inside that picture. It cannot be brought to rest. It has no ordinary rest frame. In quantum mechanics, it does not even possess a classical path in the way a bullet does. And in modern field theory, what we call a photon is not well described as a tiny, glowing marble flying through empty nothingness. Light may indeed propagate. Information may indeed be transmitted. A detector may indeed click here after a source emitted radiation there. But the old mental image, a little object moving through a passive background of space the way a baseball crosses a field, may be profoundly wrong. And that is the question of this topic. Not whether light exists, not whether its speed can be measured, not whether electromagnetism is real. Those are settled. The real question is deeper. What do we actually mean when we say that light moves? To answer this, we will need a strategy. First, we will step back and ask what motion originally meant in classical physics. We will examine the ordinary picture that works so well for stones, planets, and machines, and see why that picture feels so natural. After that, we will turn to Maxwell and the discovery that light is not merely something bright, but an electromagnetic phenomenon described by equations that already begin to strain the old intuition. Then, we will move into the crisis of the ether, because that historical failure is not a side note. It is the point where physics first began to realize that light might not need a medium in the ordinary sense at all. Next, we will confront Einstein, relativity, and the destruction of the idea that space and time are fixed containers inside which everything else simply moves. From there, we will go further still, into quantum mechanics and quantum field theory, where the photon stops looking like a tiny projectile and begins to look like something far stranger, an excitation of a field, a quantum event, something that resists every classical picture we try to impose upon it. And finally, after building all of that carefully, we will return to the sentence itself and answer it precisely. In what sense light does move, in what sense it does not, and why that distinction matters. That is the roadmap. and it matters because this topic is very easy to mishandle. One can say, "Light does not move," as a dramatic slogan. One can also say, "A photon experiences no time," and turn that into mystical nonsense. We are not going to do that. We are going to be careful. We are going to separate what is a metaphor from what is a theorem, what is a useful shorthand from what is actually permitted by the formalism. Because in physics, a sentence can be emotionally powerful and still be wrong. And this subject has exactly that danger. For instance, people often say that from the photon's point of view, emission and absorption happen at the same instant. That sentence points towards something real, but stated carelessly. It can also create a false picture. Strictly speaking, there is no valid inertial rest frame of a photon. So one of the central tasks ahead of us will be to learn how to talk about light without smuggling in images that the mathematics itself forbids. The problem is not that light is mysterious in a vague, romantic sense. The problem is sharper than that. Light forces us to confront the limits of ordinary language. Words like move, path, travel, and even object were shaped by everyday experience. They were not designed for relativistic quantum entities. And yet we keep trying to use them. Sometimes they still work as approximations. Sometimes they quietly fail. Think about how instinctively we picture a beam of light. Something leaves a source. It goes through space. It arrives at a target. That grammar is almost irresistible. Source, journey, destination. It is the grammar of arrows, bullets, and thrown stones. But throughout this topic, we are going to ask whether that grammar belongs to light at all. Because what if light is not best understood as a thing moving through space? What if that is only a rough approximation that survives at human scales? What if, at a deeper level, light is tied to the structure of space-time itself, to the propagation of the electromagnetic field, to the causal architecture of the universe, in a way that makes the old picture not merely incomplete, but conceptually misleading? If that is true, then this is not a small correction. It means the phrase "the speed of light" is not just about how fast one object goes. It may be telling us something about the very rules by which reality is allowed to update from one event to another. And that, in turn, means the subject is bigger than light. It reaches into motion, time, causality, and the nature of physical explanation itself. Because once light no longer behaves like an ordinary moving object, we are forced to ask a more uncomfortable question. Perhaps the real mystery is not light. Perhaps the real mystery is that our everyday idea of motion ever seemed universal in the first place. So let us begin there. Before relativity, before quantum mechanics, before photons, fields, and path integrals. We begin with the old world. A world in which motion seemed simple. A world in which an object could always, at least in principle, be somewhere, then somewhere else, while time passed evenly in the background. A world that made immediate sense to the human mind. Because only when we understand that older picture clearly can we appreciate how completely light breaks it. And so the first question is not yet about photons. It is more basic than that. If we want to know whether light moves, then we must first ask, What does it mean, in physics, for anything to move at all? Before we can say anything precise about light, we have to slow down and define the idea that light is supposed to challenge. That idea is motion. And for most of human history, motion did not seem mysterious at all. It seemed obvious. An object is here. Then later, it is there. Something has changed position while time has passed. That is the basic picture. A stone falls from a tower. A cart rolls along a road. A ship crosses the sea. A planet circles the sun. In every case, the mind naturally builds the same structure. There is a thing. There is a place. There is a path between places. And there is time passing while the thing follows that path. This picture became especially clear in classical mechanics. In that framework, motion means that an object has a position at each moment of time. If you know where it is now, and you know the forces acting on it, then in principle you can calculate where it will be later. The object remains the same object throughout the process. It persists continuously. It occupies one location after another. That continuity matters. Because when we imagine motion in the ordinary sense, we do not merely imagine two endpoints. We imagine the in-between. A thrown ball does not vanish from one side of the room and appear on the other. It traces a trajectory. At every instant, it is somewhere. If we could freeze time again and again, we would find it at one position, then another, then another. So classical motion contains several assumptions that feel so natural we usually do not notice them. First, there is an object that exists as an identifiable thing. Second, that object can, in principle, be at rest. Third, when it moves, it follows a definite path. Fourth, time passes for that object continuously along the way. And fifth, space is treated as the arena through which the object moves, not as something that participates in the motion itself. That last point is especially important. In the classical picture, space is the stage. Objects are the actors. The stage does not do very much. It provides distances, directions, and locations. Time, meanwhile, is the universal clock hanging above the stage. It ticks the same for everyone, everywhere. This is why ordinary motion feels so easy to understand. It fits human experience perfectly well. We live among medium-sized objects, moving at modest speeds. In that domain, this conceptual framework works extremely well. In fact, it works so well that it became tempting to assume it was not merely practical, but fundamental. Now, we need to sharpen this further. Because there is already an important distinction hiding inside classical thought, and if we miss it, the rest of the documentary will become much harder to follow. The distinction is between an object moving through a medium and a pattern propagating through a medium. Take a simple example. Imagine a cork floating on water. If the cork drifts across the pond, that is one kind of motion. The object itself changes location from one side of the pond to the other. But now imagine a water wave passing across the pond. The wave travels outward, yes, but the water does not travel outward in the same way. Individual water molecules mostly move up and down or in small local loops. The pattern advances. The medium does not migrate across the pond in the same way the pattern does. That is a different kind of phenomenon. And it matters because the word move is already doing two jobs. Sometimes it refers to a material object changing location. Sometimes it refers to a structured disturbance spreading through something that is already there. The same is true for sound. When you hear a voice from across a room, it is tempting to imagine the sound itself as a thing flying toward you. But what is really happening, in the classical description, is that air molecules oscillate locally, passing a pressure pattern onward. The pattern propagates. The air does not shoot from the speaker's mouth to your ear as one bulk flow. This difference between object motion and pattern propagation is one of the first cracks in our intuition. Because once you see it, you realize that something got from A to B does not always mean some material thing traveled from A to B in the ordinary sense. Picture a stadium wave. One person stands, then sits. The next person, media, the same. Then the next. Soon, a visible wave moves around the stadium. But no spectator runs around the arena carrying the wave with them. The pattern advances. The people stay roughly where they are. This example is valuable because it separates two ideas that everyday language often merges. A pattern can have speed. A pattern can have direction. A pattern can transfer information. And yet there may be no single object tracing the whole path in the simple classical sense. Now, classical physics understood this perfectly well for ordinary waves. No one thought the crest of a water wave was a little lump of substance that had to remain the same bit of water from beginning to end. But there was still a clear assumption underneath all of these cases. If there is a wave, then there is some medium waving. Water waves need water. Sound waves need air. Vibrations on a string need a string. So even before relativity, the old picture of motion had already split into two stable categories. On one side, objects move through space. On the other, patterns propagate through media. Both are understandable in classical terms. Both fit the idea of space as a background and time as a universal clock. And both are intuitive. This is exactly why light became such a problem. Because light seemed to share features of both categories without fitting cleanly into either one, it appeared to travel from place to place. It reflected, refracted, interfered, and diffracted. Those are wave-like behaviors. But if it was a wave, then what was the medium? And if it was a moving thing, why did it behave so unlike ordinary matter? At this stage in the story, physicists did not yet have the modern answer. But they did have the classical toolkit. So naturally, they tried to force light into one of the two familiar boxes. Either light was made of particles moving through space, or it was a wave moving through some hidden medium. That attempt makes perfect historical sense. You should not think of earlier scientists as confused. They were reasoning from the deepest successful ideas available to them. the real issue was not lack of intelligence. The issue was that nature was about to demand a third picture, one that classical intuition had not prepared them for. Before relativity, motion meant continuous change of position in a shared space, measured against a shared time. For ordinary objects, that meant definite paths. For waves, it meant structured disturbances propagating through a medium. Those were the two great classical models. Light will not remain comfortable inside either of them. But to appreciate how radical that failure is, we first need to see the moment when light stopped being merely illumination and became something much more precise. A set of equations. A self-propagating electromagnetic phenomenon. A discovery that seemed, at first, to solve the mystery completely. And in doing so, quietly created an even deeper one. If light is not an ordinary object moving through space, then is it a wave? And if it is a wave, what exactly is waving? We separated two classical ideas that usually get mixed together. A material object can move through space. A pattern can propagate through a medium. That distinction matters because, in the 19th century, light began to look less like a projectile and more like a wave. But that raised an immediate scientific problem. If light is a wave, then what exactly is waving? To understand why this question became so important, we need to step into one of the great turning points in physics. Not a turning point driven by a telescope. Not by a dramatic experiment at first, but by equations. James Clerk Maxwell did not begin by trying to explain starlight or color or vision. He began with electricity and magnetism. And from that work, something astonishing fell out. By Maxwell's time, physicists already knew many separate facts. Electric charges exert forces. Currents produce magnetic effects. Changing magnetic conditions can induce electric currents. Faraday had developed the field idea in a deep, intuitive way. Not action at a distance in the old mechanical style, but a physical state spread through space. Maxwell's achievement was to give that picture mathematical structure. The modern compact form of Maxwell's equations came later, but the physical content is the crucial thing. In vacuum, they tell us four essential facts. First, electric charge is the source of electric field. Second, there are no isolated magnetic charges in the ordinary theory, so magnetic field lines do not begin or end on magnetic monopoles. Third, a changing magnetic field generates a curling electric field. Fourth, a changing electric field generates a curling magnetic field. That fourth point deserves special care, because it is one of the most important insights in the whole story. Before Maxwell, Ampere's law linked magnetic effects to electric current. But Maxwell realized that this was incomplete. If the electric field itself changes in time, that changing field also contributes magnetically. This is the famous displacement current term. Without it, the system is incomplete. With it, the equations suddenly become capable of supporting self-propagating disturbances. Imagine a region of empty space with no charges and no currents. Nothing material is there. No wire. No air required in the theory. No vibrating string. In that vacuum region, Maxwell's equations still allow electric and magnetic fields to exist and evolve. Suppose the electric field changes. According to Maxwell's corrected law, that changing electric field generates magnetic field. Now suppose that magnetic field also changes. According to Faraday's law, that changing magnetic field generates electric field. And then that changing electric field generates more magnetic field. The system closes on itself. This is the crucial step. Light, in this picture, is not a chunk of matter thrown through space. It is not a luminous pellet emitted by a source and then carried by inertia. It is a self-sustaining electromagnetic disturbance. The electric and magnetic fields continuously generate one another as the disturbance propagates, and now comes the key result. When Maxwell's equations are combined in empty space, they naturally produce waves in the electric and magnetic fields. And the theory does something remarkable. It predicts the speed of those waves directly, using only the fundamental properties of space itself. When Maxwell calculated that speed, it matched exactly the known speed of light. That was the turning point. Light is an electromagnetic wave. That was the shock. He was not merely saying that light behaves a bit like an electrical phenomenon. He was saying something much stronger. Light is electromagnetic. Visible light is one part of a broader class of electromagnetic waves. The same theory that describes electricity and magnetism also predicts radiation propagating through space at the very speed already known for light. This is why Maxwell's result was so transformative. Before this, light was a separate mystery. After this, light became part of field theory. A beam of light was no longer just brightness moving from source to eye. It was a structured electromagnetic event. Now let us sharpen the scientific content even more. In a plain electromagnetic wave in vacuum, the electric field and magnetic field are perpendicular to each other, and both are perpendicular to the direction in which the wave propagates. Their oscillations are locked together by the equations. Neither field is merely riding passively on the other. The relationship is dynamical and mutual. This matters conceptually, because it begins to break the old intuition from part 2. Classical motion had given us two familiar pictures. Either a thing moves through space or a wave moves through a medium. Maxwell gave us something more unsettling. A wave exists, yes. It propagates, yes. But what is doing the waving is not water, not air, not any visible substance. It is the electromagnetic field itself. And yet, historically, this did not solve the problem completely. In some ways, it made the problem sharper. Because 19th century physicists were still deeply committed to the idea that a wave should be a wave in something. Sound is not free-floating. Water waves are not free-floating. A vibrating string is not free-floating. So even after Maxwell, the natural question remained: what is the underlying medium that carries the electromagnetic field? This is why the ether idea did not appear foolish at the time. It appeared reasonable. Perhaps all of space was filled with an invisible medium, subtle enough not to obstruct the planets, but real enough to support electromagnetic oscillations. In other words, physicists tried to preserve the classical grammar. If there is a wave, there must be a medium. But before we go to that crisis, notice what Maxwell had already done to the concept of light. He had quietly shifted the center of gravity from particles and objects to fields and equations. Light was no longer being explained in terms of little luminous bodies traveling through the void. It was being explained as a lawful disturbance of a field. That is a profound change. Because once the field becomes primary, the old image of a thing crossing an empty container starts to weaken. The electromagnetic field is not an object sitting inside space the way a ball sits in a box. It is a physical structure assigned throughout space itself. And a light wave is a changing state of that structure. This does not yet mean that light does not move. We are not there yet. But it does mean something important. It means that even before relativity, the deepest successful theory of light was already pushing us away from the naive image of tiny glowing bullets. Light had become, first and foremost, a field phenomenon. And Maxwell himself saw the importance of the speed that emerged from the theory. In a dynamical theory of the electromagnetic field, he wrote that this velocity is so nearly that of light that it seems we have strong reason to conclude that light itself is an electromagnetic disturbance. That sentence marks one of the great unifications in physics. Electricity, magnetism, and light were no longer separate chapters. They were different faces of one structure. But every great unification creates a new pressure point. Because now the question became impossible to avoid. If light is a wave in the electromagnetic field, then what is the ontological status of that field? Is it a property of an invisible medium? Is it a mechanical state of something filling all space? Or is the very demand for a medium about to collapse? By the end of the 19th century, physicists had reached a strange kind of success. Maxwell's equations had done something extraordinary. They had unified electricity, magnetism, and light into one mathematical structure. Light was no longer just brightness, or vision, or flame. It was an electromagnetic wave. And for a brief moment, that seemed like the end of the mystery. In reality, it was the beginning of a deeper one. Maxwell's theory implied that electromagnetic disturbances propagate through space at a speed fixed by the electrical and magnetic constants of vacuum, and Maxwell himself argued that light is precisely such a disturbance, because once you say the word wave, classical physics immediately asks a follow-up question. A wave in what? Water waves are waves in water. Sound waves are pressure waves in air. A vibration on a violin string is a disturbance of the string. So if light is a wave, then what exactly is oscillating when light crosses the vacuum between the sun and the earth? To a 19th century physicist, this was not a foolish question. If a wave exists, there must be a medium. That was not an eccentric preference. It was the pattern established by every known wave phenomenon. So physicists proposed the luminiferous ether, an invisible, all-pervading medium filling all space, subtle enough to pass through matter and planets without obvious resistance, but real enough to carry electromagnetic waves. Now pause and appreciate the burden that idea had to carry. The ether had to be everywhere, because light from the stars reaches us from every direction. It had to be extraordinarily rigid in one sense, because transverse waves usually require a medium capable of supporting sideways disturbance. But it also had to be extraordinarily intangible, because the planets did not appear to plow through it the way an object plows through air or water. It had to fill all of space, penetrate ordinary matter, remain nearly undetectable, and yet still be physically real enough to define an absolute frame of rest. That last point matters most. If the ether existed, then it was not just a carrier of waves. It was the hidden standard of absolute rest. An observer moving through the ether should, in principle, be able to detect that motion. Light traveling along the direction of Earth's motion through the ether should behave slightly differently from light traveling perpendicular to it. The difference would be tiny, but not zero. And that is the origin of one of the most famous experiments in the history of physics. Albert A. Michelson, and later Michelson together with Edward Morley, set out to detect Earth's motion relative to the ether. This was not a desperate attempt to save a failing theory. It was, at the time, a perfectly reasonable measurement to attempt. If the ether is real, then Earth should move through it as it orbits the Sun, and that motion should produce an ether wind. The instrument they used was the interferometer. Its conceptual beauty is worth understanding clearly. A beam of light is split into two parts. One beam travels along one arm of the apparatus. The other travels along a perpendicular arm. Each reflects back, and the two are recombined. If one beam took even slightly longer than the other, the recombined light would show a shift in the interference pattern. That makes the apparatus exquisitely sensitive to small differences in travel time. Now let us build the classical expectation slowly. Suppose Earth is moving through the ether. Then the arm aligned with Earth's motion should not behave exactly like the arm perpendicular to it. On the parallel arm, the light would effectively have to go upstream and then downstream against the ether wind, rather like a swimmer crossing a river with a current. On the perpendicular arm, the geometry is different, but there should still be a calculable effect. So the round-trip times should differ. And when the entire apparatus is rotated, that difference should change, producing a measurable shift in the interference fringes. This was the key prediction. Not a vague philosophical hope. A concrete optical signal. If the ether existed in the straightforward classical sense, the fringes should move when the apparatus is turned. Michelson's earlier work in 1881 and the more refined Michelson-Morley experiment of 1887 were designed precisely to look for that effect, and then came the result that changed everything. The expected shift did not appear. More carefully, the observed effect was far smaller than what the simplest ether drift picture predicted. The result was essentially null. Earth did not seem to be moving through the ether in any detectable way, at least not in the way the theory had demanded. This is one of those moments in science that can sound less dramatic than it really was. A null result can seem like nothing happened. But here, an absence became an event. The experiment was supposed to reveal the invisible medium beneath all optics. Instead, it failed to reveal it. And once that happened, the ether ceased to be a secure, explanatory foundation. Of course, physics did not surrender the ether immediately. science almost never abandons a major conceptual structure after a single blow. Instead, physicists tried to repair it. If the ether could not be detected directly, perhaps matter moving through it changed shape in just the right way to conceal the effect. This is where the Fitzgerald-Lorentz contraction idea entered the story. Perhaps objects physically contract along the direction of motion through the ether, reducing the expected fringe shift. At first glance, this sounds like a clever rescue. And mathematically, it was clever. But conceptually, notice what was happening. The theory was no longer explaining the world in a direct mechanical way. It was beginning to protect itself by postulating exactly those hidden deformations needed to hide the ether from observation. The medium was becoming less a physical entity you could discover and more a ghostly backdrop whose effects had to be inferred indirectly and patched carefully to remain invisible. This is the point where the philosophical pressure became intense. Because once a medium is posited as physically real, yet every direct attempt to detect motion relative to it fails, one must ask a harder question. Is the medium real but elusive? Or is the demand for such a medium itself mistaken? And this is where the ether crisis becomes much more than a historical anecdote. It is the first major sign that light does not fit comfortably into the old categories. If light was simply a classical wave in a classical medium, then the motion of the observer relative to that medium should matter in an ordinary way. But nature refused to cooperate with that expectation. Notice how deep the problem really is. In the old worldview, waves inherit the motion of their medium. And motion itself is measured relative to some background. The ether was supposed to provide that background for light. But if no ether wind appears, then light is left in a remarkable conceptual position. It behaves like a wave, yet resists being anchored to a detectable wave-bearing substance. One might say, there must be some deeper, mechanical explanation we have not yet found. But that hope was beginning to erode. Not because physicists had become impatient, but because the theory and the data were starting to point in a different direction. And that new direction was radical. Perhaps the problem was not that the ether had strange properties. Perhaps the deeper problem was the very assumption that light needed a medium in the classical sense at all. Perhaps the urge to ask what is waving underneath was itself inherited from too narrow an understanding of motion and waves. That is why the death of the ether matters so much to our title. It did not prove, all by itself, that light does not move. But it removed the last comfortable classical image in which light could simply be treated as an ordinary wave in an ordinary medium. The old language was losing its support. A wave remained. A speed remained. Propagation remained. But the familiar mechanical picture underneath them was collapsing, and history becomes especially interesting here, because the next step was not merely to tweak the ether theory. The next step was to ask whether the entire framework of space and time had been formulated incorrectly. Whether the failure to detect the ether was not an inconvenience, but a clue. That is the doorway to Einstein. Not Einstein as a magician who suddenly invented strangeness from nowhere, but Einstein as the thinker willing to do what few are willing to do in science: remove the hidden assumption instead of decorating it. If there is no detectable ether, perhaps there is no need for one. And if light still has the same speed in vacuum, then perhaps it is not light that must be reinterpreted within old mechanics. Perhaps old mechanics itself must give way, so the collapse of the ether is not the end of the story. It is the moment the stage itself begins to shake. Space can no longer remain a passive container. Time can no longer remain a universal background clock. Because once the ether dies, the question becomes impossible to avoid. If light is not moving through a hidden medium, then what exactly is it moving through at all? Now the story reaches its first true break. Up to this point, classical physics had been under pressure, but it had not yet collapsed. Maxwell had shown that light is an electromagnetic phenomenon. The ether had been invented to preserve the old idea that every wave must have a medium. And then the ether refused to appear when physicists tried to detect Earth moving through it. At that moment, physics faced a choice. Keep repairing the old picture, or ask whether the old picture itself was wrong. Einstein chose the second path. What makes Einstein's move so remarkable is that he did not begin by trying to explain light with some new hidden machinery. He did not invent a better ether. He did not search for a more subtle mechanical medium. Instead, he asked what would happen if we took two ideas seriously at the same time. First, the laws of physics should work the same way for all observers moving steadily, without acceleration. Second, the speed of light in empty space should come out the same for all of those observers, no matter how they move relative to one another. At first, those two ideas sound harmless, but together they are explosive. Because in the older Newtonian picture, speeds are supposed to add in the obvious way. If a train moves forward and someone inside throws a ball in the same direction, an outside observer sees the ball moving faster than the train alone. That is normal motion. It matches daily life. It feels almost too obvious to question. But light does not behave that way. If someone shines a beam of light inside a moving train, the person on the train measures the usual speed of light. And the observer standing outside, watching the train rush by, also measures the same usual speed of light. That is the problem. In the old framework, one of those observers should have measured a different result. But nature does not allow that. So Einstein recognized something profound. If the speed of light does not adjust itself to fit our old ideas of motion, then our old ideas of motion must be the things that give way. Space must change. Time must change. Simultaneity must change. The old stage on which physics had been acting for centuries could no longer remain fixed. To understand why, physicists often imagine a very simple clock made from light. Picture two mirrors facing each other, one above the other. A pulse of light bounces between them. One bounce marks one tick. In the clock's own rest frame, nothing seems unusual. The light simply goes straight up, then straight down, again and again. Now imagine that the entire clock is moving sideways past you. You are no longer traveling with it. You are watching it from outside. In your view, the light does not go straight up and down anymore. While it is traveling between the mirrors, the whole clock is sliding sideways. So the light must follow a slanted path, like a diagonal. This is the key step. From your point of view, the light has to travel a longer distance between ticks than it does from the clock's own point of view. But the speed of light is not allowed to change. That was Einstein's starting point. So if the speed stays the same and the distance is longer, then the only thing left that can change is the time. That means the moving clock must tick more slowly. Not because the clock is broken, not because the observer is fooled, not because the mechanism is malfunctioning. It ticks more slowly because time itself is no longer behaving as a universal background. This is one of the deepest moments in all of physics. Einstein did not discover that clocks are unreliable. He discovered that all physical processes that function as clocks are affected in the same way. A light clock slows down. An atomic clock slows down. A biological process slows down. It is not the device. It is the structure of time in a moving frame. Once you accept this, the Newtonian world begins to come apart piece by piece. In the old picture, time flowed equally for everyone, everywhere. Two observers might disagree about where something is, but they would agree on the underlying clock of the universe. Einstein showed that this cannot survive if the speed of light is the same for all inertial observers. There is no single universal time that everyone shares. And it gets deeper still. If time depends on motion, then the idea of simultaneity also begins to break apart. Two events that one observer says happened at the same moment may not be judged simultaneous by another observer moving differently. That is not a trick of perception. It is built into the structure of space-time itself. So now pause and notice what has happened to the idea of motion. Motion seemed simple. A thing was here, then later it was there. Space was the stage. Time was the common clock above the stage. But after Einstein, that picture is gone. Motion is no longer just change of position inside a fixed background. Motion changes how distance and time themselves are related. And this is exactly why light is not just another moving object. A stone can be brought to rest. A cart can be brought to rest. A planet has a meaningful velocity relative to some chosen frame, and you can always imagine another observer moving alongside it. But light resists that treatment from the beginning. Its speed does not behave like an ordinary speed inside the old system. It is the fact that forces the system itself to be rebuilt. This is why relativity is not really a theory about light alone. It is a theory about space, time, and causality, discovered because light refused to fit the old rules. Light did not politely take its place inside Newtonian mechanics. It shattered Newtonian mechanics at its foundation. And the effects are not merely theoretical. Fast-moving particles created high in Earth's atmosphere survive longer than they would if time flowed for them the same way it flows for us at rest. Extremely accurate clocks placed on aircraft or satellites drift relative to clocks on Earth in precisely the way relativity predicts. Modern navigation systems would fail if these effects were ignored. So when we say that Einstein changed physics, we should be very precise about what changed. He did not merely add a strange correction factor to old mechanics. He showed that the old concept of motion was never fundamental. The world is not built from objects moving through an absolute space, while an absolute time ticks for all of them equally. The world is built from events related within space-time, and light marks the structure that those relations must obey. That is why the title of this topic is no longer just provocative. It is becoming scientifically meaningful. The sentence, "light moves," is still usable in ordinary language. Light goes from the sun to Earth. Light goes from a laser to a wall. But after relativity, we can already see that it does not move the way a baseball moves, or the way a train moves, or the way any ordinary object moves. We are now ready to ask a much sharper question. In the previous part, relativity forced us to abandon the old idea that motion happens inside a universal space and a universal time. Light was the reason. Its speed refused to behave like the speed of ordinary things. And once Einstein took that seriously, time itself had to become flexible, and simultaneity had to become relative. But all of that now leads to a more dangerous thought. If every ordinary object can, at least in principle, be brought to rest by moving alongside it, then why not light? Why can we not simply imagine an observer chasing a beam until the beam finally appears frozen? That is one of the most natural questions in all of relativity. And it is also one of the most revealing. Because the answer is not merely that this is difficult. It is not merely that we lack a good enough rocket. The answer is that the question itself breaks the structure of the theory. For an ordinary object, the idea of a rest frame is straightforward. If a car is moving down the road, someone inside the car can treat themselves as at rest. If a train passes a platform, passengers on the train can describe the train as stationary and the platform as moving backward. That is not an illusion. It is built into the principle of relativity. Motion at constant speed is relative, so every massive object can be assigned a frame in which it is at rest. But light is not like that. A photon is never observed at rest. More than that, special relativity does not permit a valid inertial frame in which a photon is at rest. There is no lawful way, inside the theory, to move into step with a light beam and make its speed become zero. People often say things like, "From the photon's point of view, no time passes," or "For light, emission and absorption are the same moment." Those phrases are trying to point towards something real, but if we say them too casually, they can create a false picture. Strictly speaking, a photon does not possess an ordinary rest frame. So when someone says, "From the photon's point of view," they are using an informal shortcut, not describing a legitimate coordinate system that physics allows us to build. And that distinction matters. To see why, think about how relativity compares different observers. One inertial frame can be related to another by a transformation that depends on their relative speed. As long as that relative speed is less than the speed of light, everything works. Distances and times change in a definite, consistent way. But the moment you try to push that relative speed all the way to the speed of light itself, the structure stops giving sensible results for a physical observer. In other words, the theory lets you compare one slower-than-light observer to another slower-than-light observer. It does not let you promote light itself into the status of an ordinary observer with a valid rest frame. This is one of the deepest ways in which light is unlike any familiar moving thing. A baseball can slow down. A train can stop. A spacecraft can, in principle, drift alongside another spacecraft until there is no relative motion between them. But a photon does not belong to that family of objects. It does not pass through a sequence of slower and slower states on the way to rest. Rest is simply not one of the physically allowed states for light. For ordinary matter, we can talk about the time measured along the object's own history through space-time. That is what a clock moving with the object would register. If you carry a watch on a plane, or on a spaceship, or in your hand while walking, that watch records the time along your path. This is the object's own elapsed time, built into its motion through space-time. For light, something very different happens. Along the path traced by light in space-time, the elapsed time of that kind is zero. That is the precise statement that popular language is usually trying to reach. Not that a photon owns a little wristwatch that has stopped. Not that a photon has a human-like perspective. But that the kind of elapsed time associated with ordinary clocks does not accumulate along a light-like path. This is why the casual sentence sounds so strange. Light can cross enormous cosmic distances by our clocks. The sunlight reaching Earth left the sun about 8 minutes ago in Earth's frame. Light from distant galaxies may have been traveling for millions or billions of years in the cosmological frame we use to describe the expanding universe. And yet the path of light is not like the path of a massive traveler who sits inside time in the ordinary way, aging from one moment to the next. That difference is exactly why the idea of a photon's rest frame is so misleading. A rest frame belongs to things that can sit still and carry clocks in the ordinary relativistic sense. Light does neither. Now, it is important not to overstate this. We should not jump from light has no rest frame to light does not propagate, or light is everywhere at once, or any other dramatic slogan. Those are usually examples of language outrunning the theory. By our measurements, light absolutely does propagate. It takes time to travel from a source to a detector in a given frame. We can measure that time. We can build technologies around it. Communication delays in space missions are real. Signals from the sun are not instantaneous. So the point is not that travel disappears. The point is subtler. The travel of light is not the travel of an object that could, even in principle, be brought into ordinary rest. And because of that, the words we normally use for motion begin to lose their familiar meaning. This is why the title of our documentary is beginning to sharpen. Light doesn't move at all is not literally true if taken in the crudest possible way. Light does go from here to there. It does arrive later than it was emitted in a given frame. But the sentence does point toward a real fracture in our intuition. Light does not move in the way moving things normally move. And once that is understood, another major difference comes into focus. For an ordinary object, motion is layered on top of existence. The object exists, and then it may move or not move. For a photon, that classical distinction becomes unstable. The photon is never first given to us as a little object sitting there, ready either to rest or to move. From the start, it appears as something fundamentally tied to propagation at the invariant speed. This has consequences for the way we imagine reality. In everyday thought, rest feels basic and motion feels secondary. First a thing is there, then perhaps it begins to move. But with light, that ordering fails. There is no deeper, more natural condition in which the photon is simply sitting still. The very idea of the photon is bound up with light-like propagation. That is already enough to break the old Newtonian imagination. But the story will go even further. Because so far, we have still been speaking as though a photon were at least some kind of tiny object with a trajectory, even if a very unusual one. And quantum mechanics is going to take that remaining comfort away. Because once we enter the quantum world, the trouble is no longer only that light has no rest frame. The trouble is that light does not even behave as though it follows a single classical path, like a miniature bullet. If a photon cannot be at rest in any physical frame, then what kind of thing is a photon really? At this point, most of the old picture has already been weakened. We know that light cannot be treated like an ordinary moving object inside Newtonian space and time. We know that a photon has no ordinary rest frame. We know that relativity does not permit us to catch up to light and watch it stand still. But there is still one piece of intuition left, and it is one of the hardest to let go of. That intuition is the image of the photon as a tiny bullet. A little particle of light. A luminous dot. A miniature object fired from a source, rushing through space, eventually striking your eye or a detector. It is a powerful image because it feels concrete. It gives the mind something to hold. And in everyday speech, it seems harmless enough. But the deeper physics becomes, the less that image survives. Not because photons are unreal, not because light is vague or mystical, but because the bullet picture quietly smuggles in almost everything that modern physics has already forced us to abandon. A bullet is the perfect classical object. It has a definite location at each moment. It has a path. It can move faster or slower. It can, in principle, be brought to rest. It persists as the same little thing all along its route from source to target. And that is exactly the problem. A photon does not fit that description. To see why, begin with the most basic contrast. A bullet can exist in a resting state. Even if it is currently flying through the air, we know what it would mean for it to be motionless. We could place it on a table. We could carry it in a box. But a photon has no such state. There is no physically meaningful version of a photon sitting still, waiting to begin its journey later. That already tells us something important. The photon is not a familiar object first, and a moving object second. Its very identity is tied to propagation. It never enters the world in the calm, classical way a bullet does. Now, go one step deeper. A bullet has mass. That mass is part of why it behaves the way it does. It resists acceleration. It can exchange momentum with other objects in the ordinary mechanical sense. A photon also carries energy and momentum. This is crucial, and we must not lose it. Light can push. Light can transfer energy. Light can eject electrons from matter. But it does so without being a massive little pellet. This is one of the reasons the bullet picture is so seductive. Because photons do arrive in localized detection events, a detector clicks here, not everywhere. A photosensitive surface records a hit at one spot, not as a blurry fog over the entire apparatus. And the mind naturally says, then surely a tiny thing must have flown to that spot. But that conclusion turns out to be too quick. A localized detection does not automatically mean a classical miniature object followed a classical miniature path. That is exactly the trap quantum mechanics is going to expose. Before we get there, let us stay for a moment with the classical image and see how much it assumes. If you imagine a photon as a bullet, you are imagining something with a single, well-defined route from beginning to end. You are imagining that at every instant it is somewhere precise, traveling along some narrow line through space. You are imagining that if only your instruments were good enough, you could track that route the way you track a projectile. But the evidence does not support that picture. In fact, the closer we look, the more that picture becomes a liability rather than a help. Even before quantum mechanics fully enters, light already resists the bullet model through its wave behavior. Interference is the obvious clue. Diffraction is another. Reflection and refraction can be described in ways that still tempt us toward ray-like language, but interference is much harder to force into a simple pellet story. Whenever light produces patterns that depend on phase, overlap, and cancellation, the bullet picture begins to look deeply incomplete. This is the historical tension that ran through early modern physics. On the one hand, light clearly behaves in some contexts as though energy arrives in discrete exchanges. On the other hand, it also behaves in many contexts as though it is spread out and wave-like. If you cling too tightly to the idea of tiny bullets, you lose the wave phenomena. If you cling too tightly to the idea of a smooth classical wave, you lose the discrete detection events. And so the photon begins to emerge as something that does not belong comfortably to either old category. Not a little marble. Not a little bead of glowing dust. Not a miniature cannonball of brightness. There is another reason the bullet analogy fails, and it is subtle. A bullet is one thing, and the space through which it moves is another. The bullet is the actor. Space is the stage. But modern physics has already begun to teach us that light is much more tightly bound to the structure of the electromagnetic field itself. In other words, the photon is not best imagined as a little object traveling through a passive emptiness. It is connected to a field that already exists throughout space. That distinction matters. Because once a phenomenon is fundamentally a field excitation rather than a tiny classical object, the whole grammar changes. The language of a thing traveling through nothingness starts to lose its grip. Think of the difference this way. If you throw a pebble across a pond, the pebble is distinct from the water. But if a ripple spreads across the pond, the ripple is not some second object riding on top of the water like a passenger. It is a changing state of the medium. Now, the photon is not simply a classical ripple in a classical medium. That would take us back to the ether, and we have already buried the ether. But the comparison still helps at the level of intuition. The deeper theory will not ask us to imagine a bead crossing emptiness. It will ask us to imagine a quantized disturbance of a field. And that is a very different ontological picture. A bullet carries its identity as a compact object from one place to another. A field excitation is not best understood that way. It is something happening in the field, not something detached from it. Now let us make the contrast even sharper. Suppose you shine a weak beam of light onto a detector so faint that individual detection events can be separated. The detector does not report a continuous smear. It clicks one event at a time. This is the moment when many people instinctively say, "There, that proves the photon is a tiny particle after all." But not so fast. What it proves is that the interaction with matter is quantized. Energy is exchanged in discrete amounts. That is a real and essential fact. But it does not yet tell you that between emission and detection, the photon behaved like a microscopic bullet tracing a single classical route. That distinction is absolutely central. A discrete outcome is not the same thing as a classical trajectory. Quantum theory forces us to separate those ideas. This is why the word particle can be dangerous if left unexplained. In everyday language, particle means a tiny bit of stuff, a grain, a speck. But in modern physics, when we say photon is a particle, we do not mean a miniature pebble of light obeying ordinary mechanical intuition. We mean something much more abstract and much more precise, a quantum entity associated with discrete, localized interactions and definite amounts of energy and momentum. So the word remains, but the old imagery has to go. That is one of the recurring lessons of this whole topic. The language survives longer than the intuition that originally gave rise to it. We keep old nouns, but their meanings become stranger under pressure. Now let us return to the title for a moment. Why does all this matter for the phrase, "light doesn't move at all"? Because as long as you imagine the photon as a tiny bullet, the title sounds obviously absurd. Of course, the bullet moves. That is what bullets do. But once the bullet image begins to fail, the sentence stops sounding merely provocative and starts sounding like a clue. Not a literal denial of propagation, but a warning that classical motion is the wrong conceptual model. The photon does not move the way a bullet moves. It is not a compact bit of material substance flying through a neutral background while carrying an ordinary history through time. Whatever a photon is, it belongs to a deeper framework than that. And in the next step, quantum mechanics will force that conclusion beyond recovery. Because the real collapse of the bullet picture comes when we ask a brutally simple question. Through which path did the photon actually go? Classically, every bullet has an answer. quantum mechanically, light will refuse to give one in the way we expect. Up to this point, one might still try to save some fragment of classical intuition. One might say, yes, light is strange. Yes, it has no rest frame. Yes, the photon is not a tiny bullet in the ordinary sense. But perhaps, underneath all that, it still goes through space, along one actual route. That hope does not survive the double-slit experiment. This experiment matters so much because it asks a brutally simple question. If light goes from a source to a screen, and if there are two openings in between, then through which opening did it go? In classical thinking, that question is completely reasonable. A thrown pebble goes through the left opening or the right opening. A bullet goes through one or the other. Even if you do not know which one, you still assume there is a fact of the matter. The object had a path. The path was definite. Your ignorance does not erase the path. That is the classical attitude. And the double-slit experiment is one of the cleanest demonstrations that light does not obey it. Let us build the setup carefully. You have a source of light. In front of it is a barrier with two narrow slits. Behind the barrier is a screen that records where the light arrives. If you close one slit and leave only the other open, you get a bright region lined up with that slit. If you do the reverse, you get a similar bright region from the other slit. So far, nothing shocking. Now classical common sense makes a prediction. If both slits are open, you might expect the final pattern to be just the sum of those two single-slit patterns. More light through the left slit, plus more light through the right slit. Two contributions added together. That would be the natural result if light consisted of little independent objects choosing one side or the other. But that is not what happens. What appears on the screen is an interference pattern. Bright bands, dark bands, bright again, dark again. In some places, opening the second slit makes the screen brighter. In other places, opening the second slit makes the screen darker. That is already enough to tell you that the two possible routes are not behaving like two separate streams of tiny pellets. Because pellets do not cancel each other into darkness. Ordinary particles can add. They do not produce regions where adding a second route removes arrivals altogether. But waves can do that. When two wave contributions line up in one way, they reinforce. When they line up in another, they cancel. So at first glance, the lesson seems simple. Light is a wave. End of story. But then the experiment becomes even more unsettling. Because you can dim the source so far down that detections happen one at a time. Not a bright continuous beam. Not a flood. Single events. One click here, then later another click there, then another. Each individual detection is localized. It appears at one spot, not smeared across the whole screen. And yet, after many such individual events accumulate, the same interference pattern emerges. This is the real shock. Each detection looks particle-like, but the full distribution looks wave-like. And that means the old language begins to break from both sides at once. If you insist that the photon is only a classical wave, you cannot easily explain why each event lands as a discrete, localized hit. If you insist that the photon is only a classical particle, you cannot explain why the accumulated pattern shows interference, including dark bands where the probability of arrival is suppressed. So the question becomes sharper. What is interfering with what? Classically, if each photon is a tiny object, then each one should pass through slit A or slit B. But the interference pattern tells you that the final probabilities depend on both openings being available in a way that cannot be explained by a hidden choice between two ordinary paths. This is where quantum mechanics forces a conceptual change. It does not tell us that the photon secretly had one classical path and we were merely too clumsy to discover it. It tells us that before measurement, the correct description is not a single definite trajectory of the classical kind. That statement must be handled carefully. It does not mean anything goes. It does not mean physics gives up. It means the theory assigns something more subtle than a path. It assigns amplitudes associated with the possible alternatives, and those amplitudes combine before a detection event occurs. In simpler language, the theory does not ask, which slit did the photon really choose, behind our backs? It asks, how do the different possible routes contribute to the final outcome? That is a completely different way of thinking. The classical mind wants a route first and a result second. Quantum theory gives you the structure for predicting results without granting the photon a classical route in between. And then comes the most important twist of all. If you place detectors at the slits to determine which slit the photon goes through, the interference pattern disappears. This point cannot be overstated. The very act of arranging the experiment so that the path becomes knowable changes the final pattern. Once the setup distinguishes slit A from slit B in a path-definite way, the dark and bright interference structure collapses into a pattern more like an ordinary mixture of alternatives. So now, the classical question, which path did it really take all along, starts to look less like a deep question and more like a category error. Because the answer depends on the physical arrangement of the experiment. When the setup preserves the conditions for interference, the photon is not described as having one classical path. When the setup destroys that interference by extracting path information, the behavior changes. People say, the photon went through both slits. Others say, the photon went through neither, in the classical sense. Others say, the question has no meaning before measurement. Different interpretations phrase this differently. But what all serious versions agree on is the central point. The photon is not behaving like a miniature bullet with a hidden ordinary route from source to screen. That is the key conclusion. Whatever light is, it is not a little object that simply travels one narrow track through space in the classical way. And once you accept that, the topic begins to sharpen again. Light doesn't move at all is still not the literal final statement we would teach in a textbook. But the sentence is doing useful work. It is breaking the reflex to imagine motion as a tiny object occupying one position after another along a single path. Because in the double-slit experiment, that picture is not merely incomplete. It gives the wrong intuition. This is also why the photon cannot be saved by saying, "Fine, then it is just a very weird, tiny particle." No. The problem is deeper than weirdness. The problem is that the very concept of a path has changed status. For a classical particle, the path is part of the basic ontology. For a photon in a quantum experiment, the path is not always a meaningful pre-existing fact of the same kind. And that means the phrase, "the photon went from the source to the screen," has to be treated with more care than everyday language suggests. Yes, the source emitted. Yes, the detector later clicked. Yes, there is a well-defined experimental arrangement connecting those two events. But between them, the photon is not faithfully represented by the image of a tiny bead tracing one hidden line through space. And in one sense, that feeling is honest. Our minds were trained on stones, arrows, shadows, and falling bodies. We were not trained on quantum amplitudes. But the lesson is not that physics has stopped making sense. The lesson is that it makes sense in a deeper way than ordinary imagery can capture. The theory predicts the pattern. The experiment confirms it. What fails is not the science. What fails is the old mental picture. If the photon does not follow one classical path, then what are we supposed to imagine instead? What kind of thing can produce localized detections, interference patterns, and a total collapse of ordinary path language all at once? The next answer will take us beyond simple wave talk and beyond simple particle talk. It will take us to the idea that light is not a little object moving through empty space, but a quantized excitation of a field already present everywhere. At this point, something important has happened. Not all at once, but step by step. We have lost the classical idea of motion. We have lost the idea of a rest frame for light. We have lost the idea that a photon follows a single definite path like a tiny projectile. And now a deeper question stands in front of us. If light is not a little object traveling through space, then what exactly is it? This is where modern physics changes the question itself. Instead of asking what the photon is made of, it asks what structure of the universe the photon belongs to. The answer begins with a quiet but radical shift. Empty space is not empty in the classical sense. It is not a passive stage on which things move. According to modern field theory, space is filled with fields. Not substances in the old mechanical sense. Not invisible fluids like the ether once imagined. But physical entities that assign values to every point in space and time. Among these, one field matters for our story more than any other. The electromagnetic field. You have already seen it, in a way, back in Maxwell's theory. Electric and magnetic fields were introduced as quantities that exist throughout space, not just at the location of charges. They evolve. They influence one another. They can carry energy and momentum. And crucially, they can propagate as waves. But Maxwell's theory was still classical. It described the field as a smooth, continuous structure. A wave could be as weak or as strong as you like, varying continuously. There was no built-in notion of discreteness. Quantum theory changes that. It tells us that the electromagnetic field is not only a continuous entity, it also has quantized modes of excitation. And what we call a photon is one of those excitations. Now we have to be careful again, because this is the point where many explanations slip back into the old imagery. They say, a photon is like a little particle riding on a wave. That is not correct. The photon is not something separate from the field. It is not a bead moving through a background that exists independently of it. The photon is a state of the field itself, not a traveler inside the field, not a passenger, not an object moving through something else, but a specific, quantized way in which the field can be excited. To build intuition, we can use a comparison, but we must keep its limits in mind. Think of a stadium wave again. The wave moves around the stadium, but no single spectator carries the wave from start to finish. The pattern propagates through the system. Now, the electromagnetic field is not a crowd of people, and the analogy is imperfect. But it helps us separate two ideas. There is the underlying structure, the field, and there are the patterns of excitation that move through it. In classical physics, those patterns were continuous waves. In quantum physics, those patterns can appear in discrete units. A photon is one such unit. And now we can revisit everything we have learned so far and see it from a new angle. Why does light show interference? Because the field supports wave-like superposition of its excitations. Why do we get discrete detection events? Because the field exchanges energy with matter in quantized amounts. Why does the photon not behave like a tiny bullet with a definite path? Because it is not a localized object traveling through empty space in the classical sense. It is a quantum excitation whose behavior is governed by the structure of the field. And now we can approach the title again, but from a much stronger position. When we say light moves, what we are really describing is the propagation of a disturbance in the electromagnetic field. A change here influences the field there after a certain time delay. Energy and information are transferred. But the old mental image, a tiny object flying from one point to another, is no longer the right foundation. That image belongs to classical particles moving through a passive background. In the field picture, there is no such separation. The field is already present everywhere. The photon is not a traveler crossing emptiness. It is a structured change of something that already fills space. This is why the phrase, "light doesn't move," begins to take on a new meaning. It does not mean that nothing propagates. It does not mean that signals are instantaneous. It does not mean that causality is broken. It means that the classical picture of motion, an object carrying its identity from place to place through an empty stage, is not the right way to think about light. What propagates is not a tiny object. What propagates is a pattern of excitation in a field. And this resolves several tensions at once. The wave behavior is natural because fields support wave-like structures. The particle-like detection is natural because the field exchanges energy in discrete quanta. And the absence of a classical path is no longer surprising, because the underlying entity is not a classical object that must trace such a path. Now, there is still one subtlety left. Even in this field picture, we still talk about light traveling at a speed, the speed of light. We still say that signals take time to propagate. We still measure distances and delays. So, what is this speed, if not the speed of a tiny object moving through space? This question takes us to one of the deepest insights of relativity. The speed of light is not just a property of light itself. It is a property of space-time. It defines the maximum rate at which influences can propagate. It sets the structure of cause and effect. It separates events that can influence one another from those that cannot. In that sense, light is not merely something inside the universe. It is a manifestation of how the universe itself is structured. And that brings us to the final layer of the story. If light is not a tiny object, and not even just a wave in a medium, but a quantized excitation of a field that reflects the structure of spacetime, then what does it really mean to say that light goes from one place to another? Because now, the question is no longer about paths. It is about how the universe updates itself from one event to the next. We are now standing at the edge of the final conceptual shift. Up to this point, we have stripped away almost every piece of the old picture. Light is not an ordinary moving object inside Newtonian space and time. A photon has no ordinary rest frame. It does not behave like a tiny bullet. And in the quantum world, it does not travel along one definite classical path in the way our everyday intuition demands. When physicists say that light goes from A to B, what do they actually mean? Because clearly something happens. A source emits radiation. Later, a detector clicks. A telescope receives light from a distant star. A fiber optic cable carries a signal from one city to another. We are not dealing with illusion. We are not denying propagation. We are not claiming that the world is static and only appears dynamic. Something really does connect emission and detection. But the connection is not a classical journey. That is the key point of this entire part. Light can connect events without behaving like a little traveler marching through space, one step at a time, along a single hidden road. This is where Richard Feynman gave physics one of its most powerful ways of thinking. Not because he made the world stranger than it was, but because he gave us a language that matched the strange behavior nature was already showing us. In the old picture, the question is simple. A thing starts at A. It follows a path. It arrives at B. If you know the initial conditions well enough, and you know the forces, then in principle there is one real trajectory the object follows. But in quantum physics, that is not how the calculation is built. The theory does not begin by assigning the photon one hidden classical root and then asking us to uncover it. Instead, it asks us to consider all the different ways the connection between A and B can contribute to the final outcome. This idea can sound almost impossible the first time you hear it, but let us slow it down carefully. Suppose light is emitted at one place and later detected at another. Classical intuition says there must be one actual route in between, even if we do not know it. Quantum theory says that this demand is already too classical. Instead of a single route, the theory assigns a contribution to each possible route compatible with the setup. Some of those contributions reinforce one another. Some oppose one another. And when they are all taken together, they determine the probability that the photon is detected at a particular place. This is why the double-slit experiment behaves the way it does. The final pattern is not built from tiny particles, each secretly choosing one slit in the old classical sense. It is built from the way the possible alternatives combine before the detection occurs. Now, it is very important not to turn this into mythology. Saying all paths contribute does not mean the photon is a little ghost physically wandering through every absurd route in the same storytelling sense that a traveler explores roads on a map. It means that the quantum description is not organized around one classical trajectory. The path language survives only as a way of talking about the possible contributions to the amplitude for the final event. And this gives us a much better answer to the phrase, light goes from A to B. It does not mean that a tiny object, identical in the classical sense at every instant, traces one pre-existing hidden line through space. It means that the electromagnetic field and its quantum excitations allow a connection between those two events, and the probability structure of that connection is built from the full quantum setup, not from a single classical road. In other words, the photon is not best understood as carrying a little tag that says, "I took this route and no other." The theory gives us something more subtle and more powerful. It gives us a rule for calculating outcomes. And when we use that rule, the experiments come out right. This is one of the deepest turning points in the whole story. In classical physics, explanation often means telling a detailed story about what the object was doing at each moment in between. In quantum physics, explanation often means giving the structure that correctly predicts how events are related, even when the old in-between story no longer exists in the classical form we want. That can feel unsatisfying at first. The human mind wants the movie, not just the rule. We want to imagine the little thing leaving the source, crossing the gap, and arriving at the target. But nature does not always grant us that movie. Sometimes it gives us something stricter. A formal structure. A set of allowed relations. A way outcomes depend on possible alternatives. Light doesn't move at all is not a textbook sentence. It is not the way a physicist would write the first line of a lecture note. But it is doing an important job. It is tearing us away from the wrong mental picture. Because what has now become unmistakable is this. Light does not go from A to B the way a thrown stone goes from A to B. It does not go from A to B the way a train goes from one station to another. It does not go from A to B the way a bullet goes from a barrel to a wall. Those stories all depend on the classical idea of a continuously existing object with a definite position at each moment and a single actual path between endpoints. And that is exactly the picture modern physics has now taken away. So what remains? What remains is propagation without a classical journey. Connection without a tiny traveler. Transfer of energy and information without the old image of a miniature object marching through empty space as though the universe were a giant mechanical stage. And this also helps us understand why classical light rays work as well as they do in everyday life. When the wavelength is small compared with the scales we care about, and when the environment is simple enough, the quantum description produces a very strong approximation that looks like a ray. This is crucial. The ray picture is not useless. It is not false in the everyday engineering sense. It is an emergent approximation. That is why lenses work. That is why mirrors work. That is why we can trace beams in optics and get excellent answers. But an approximation is not the deepest ontology. The ray is what the deeper theory looks like when the conditions are right and the quantum complexity settles into a stable classical pattern. This point matters because many people assume that if the classical image works often, it must therefore be fundamental. But physics repeatedly teaches the opposite lesson. What works at our scale is often the large-scale shadow of something much stranger underneath. So when we say a beam of light crosses a room, that sentence is useful. It is operationally correct. It tells us what devices to build, where to put a detector, how long to wait for a signal. But if we ask the deeper question, what kind of crossing is this exactly? Then the answer is no longer classical. What crosses is not a tiny object with a single hidden route. What appears instead is a quantum field process whose outcomes are shaped by the full set of physically relevant alternatives. This is also why the phrase, "the photon took this path," has to be used with extreme care. Sometimes, in a controlled approximation, that language is fine. In other contexts, especially when interference matters, it becomes positively misleading. Move. Path. Travel. Particle. All of them survive. None of them mean quite what they first seem to mean. We have reached a place where the title can finally be answered with precision instead of provocation. In one sense, yes, light moves. By our clocks, it takes time to get from source to detector. Signals propagate. Causality is respected. But in the deeper sense that matters for fundamental physics, no, light does not move the way anything in ordinary life moves. Not as a classical object. Not with a rest frame. Not with one fixed path. Not as a tiny traveler crossing a passive void. And that means the final question is now ready to be asked. After Maxwell, relativity, quantum mechanics, and field theory, in what precise sense can we finally say that light does not move at all? Not as a slogan, not as a trick, not as a mystical sentence designed only to sound profound, but as a precise conclusion reached step by step. The question was never whether light exists. It was never whether light propagates. It was never whether a beam can go from a source to a detector. All of that is real. All of that is measurable. All of that remains true. So let us begin there. In the ordinary practical sense, light does move. Sunlight takes time to reach Earth. A signal sent through space does not arrive instantly. A laser pulse crosses a room after emission, not before. If that is all we mean by motion, that one event happens here and a related event happens later there, then yes, light moves. But that answer is only the surface. Because the whole point of this topic was that light does not move in the way ordinary things move. A thrown stone moves by occupying one place after another along a path. A train moves by carrying its mass through space, while time passes for it continuously in the ordinary relativistic sense. A bullet can be imagined at rest before it is fired, and again after it stops. Every one of those examples belongs to a familiar family of motion. Light does not belong to that family. A photon cannot be brought to rest. It has no ordinary rest frame. It is not a classical object that first exists quietly and then happens to start moving. From the beginning, its very description is tied to propagation at the invariant speed that defines the causal structure of space-time. So already, in the relativistic sense, light does not move the way a massive thing moves. And then quantum mechanics pushes the conclusion further. If you insist on imagining a photon as a tiny bullet traveling along one definite hidden route from source to detector, the theory stops matching the experiment. The double-slit experiment makes that impossible to ignore. The photon does not behave as though it always possessed one classical path in the old sense. The theory does not require us to tell that classical in-between story. It requires something subtler, a quantum structure in which the possible alternatives contribute to the final outcome, and the detection appears only at the end as a localized event. So in the quantum sense, light also does not move the way a classical particle moves. And then field theory completes the transformation. The photon is not best understood as a tiny object wandering through an empty stage called space. It is a quantized excitation of the electromagnetic field. That changes the grammar completely. What propagates is not a miniature bead crossing emptiness. What propagates is a structured disturbance of a field already present throughout space. So, in the field-theoretic sense, light does not move the way a separate object moves through a background. And now we can finally assemble the full answer. Light does move, if by move we mean that electromagnetic influence propagates from one event to another in finite time, respecting the causal structure of spacetime. Light does not move, if by move we mean that a tiny classical object with a definite path, an ordinary rest state, and a continuous traveler's history passes through empty space the way stones, trains, and bullets do. That is the distinction. And it is the whole heart of the topic. The sentence, "light doesn't move at all," is therefore not literally correct in the shallow sense. Light does propagate. Detection happens later than emission in a given frame. Communication delays are real. But the sentence becomes deeply revealing when it is heard as a warning. A warning that the ordinary human picture of motion is the wrong model for light. Light is not just one more moving thing inside the universe. It is bound up with the structure of the universe itself. Its speed is not merely a fast speed among other speeds. It marks the limit at which cause and effect can be connected. It defines the geometry along which massless influence propagates. Its quantum behavior is not merely weird particle behavior. It reveals that the world is not built at its deepest level from tiny classical objects tracing neat little lines through a passive void. And its field nature tells us something even more profound. The old idea of a thing traveling through nothingness is not fundamental. What is fundamental is the field, the structure, the allowed pattern of excitation, the relation between events. That is why light has been such a faithful guide throughout the history of physics. Again and again, it refused to fit the categories we most wanted to keep. It refused to behave like a Newtonian projectile. It refused to sit inside a universal time. It refused to rest. It refused to carry a single classical path through the quantum world. And each refusal taught us something larger than light itself. Maxwell taught us that light belongs to the electromagnetic field. Einstein taught us that light exposes the true structure of space-time. Quantum theory taught us that light cannot be forced into the old story of little objects traveling along hidden routes. Quantum field theory taught us that the photon is not a tiny traveler in space, but a quantized excitation of a field woven into the fabric of physical reality. When someone says, light moves, physics answers, yes, but not as a classical object. When someone says, light does not move at all, physics answers, not literally, but you are touching a real truth, the truth that light escapes the ordinary grammar of motion. And perhaps that is the deepest lesson here. The universe is not obligated to organize itself around the categories that feel most intuitive to us. Object, path, rest, travel. These are useful human words. They are not sacred. Light forced us to discover that, not by becoming vague, but by becoming precise. And once we accept that precision, the title transforms. It stops being a dramatic provocation and becomes a philosophical summary of everything we have learned. Light does not move at all. If what you mean by movement is the old human picture of a little thing carrying itself through a silent stage of space, while time flows the same for everyone, that world is gone. Light helped destroy it. What replaced it is stranger, but also truer. A universe made of fields, events, probabilities, causal structure, and space-time relations. And in that universe, light is not merely a traveler. It is one of the clearest expressions of the rules by which reality is allowed to unfold. So the next time you see sunlight on a wall, or a star in the night sky, or the glow of a screen in a dark room, you can still say that light has arrived. That sentence is useful. It is operationally true. But beneath that ordinary sentence sits a far deeper one. What has arrived is not a tiny luminous bullet that crossed an empty stage in the old classical way. What has arrived is the endpoint of a propagation allowed by the electromagnetic field, by quantum law, and by the geometry of space-time itself. And that is why light has always felt so strange. It is not because light is less real than ordinary objects. It is because light is more revealing. It reveals where common sense ends. It reveals where language begins to fail. And it reveals that the universe, at its deepest level, is not built to satisfy the imagination we inherited from everyday life. As Richard Feynman once said, I think I can safely say that nobody understands quantum mechanics. And perhaps that is not a confession of defeat. Perhaps it is a reminder of honesty. Because the real triumph of physics was never that it made the universe feel familiar. The real triumph was that it taught us how to follow the universe even when familiarity breaks. And light was one of our greatest teachers. So if someone asks you, at the end of all this, whether light really moves, the most honest answer is this. Yes, it propagates. Yes, it connects events across space and time. But no, it does not move the way you once thought movement had to work. And that difference changes everything. Before we close, thank you for staying on this journey. For your time, your curiosity, and your willingness to think a little deeper. If this changed how you see the universe, even just a little, then it was worth it. Thank you for being here. I'll see you in the next journey.